wabarakatuh. So now we look at another topic. This is under chapter 5, time homogeneous. Like I mentioned in the previous class, one of the special case for the time homogeneous is the Poisson processes. So now we recall back what we have learned in the statistic subject, where one of the statistical distributions that you have learned is Poisson distributions. So Poisson distributions and the Poisson process, where Poisson behavior is so pervasive in natural phenomena, and the Poisson distributions is so amenable to extensive and elaborate analysis, has to make the Poisson process a cornerstone of stochastic modeling. So, if you look at here under subtopic 1.1, the Poisson distributions, where this is the equations for Poisson distributions that you have learned in the statistic subject, where the Poisson distributions here, instead of usually you will say that parameter is equals to lambda, right? But this textbook, they just say that the parameter is equals to mu. Sama sahaja. The Poisson distributions with parameter mu, which is greater than 0, is given by equations 1.1, where you know that the equation for the Poisson distributions is e to the power of negative mu times with negative mu to the power of k divided by k factorial for k equals to 0, 1, and so on. So we let x be a random variable and having Poisson distributions under equations 1.1, then you need to find your expected value or mean, where mean is actually your first moment. So this is the equations in order to get expected value of x for random variable having Poisson distributions, where you can see that the mean or expected value for Poisson distributions is equals to mu, and same goes to the variance, where in order to find the variance, you need to determine the second moment. So the second moment, ex squared is mu squared plus mu. Then you want to find your variance for Poisson distributions, where variance for Poisson distributions is also equals to mu. So the Poisson distribution has the unusual characteristic that both the mean and the variance are given by the same value mu. So here we have two fundamental property of the Poisson distributions, which will arise later in the variety of forms concern the sum of independent Poisson random variables and certain random decompositions of Poisson phenomena. So under these Poisson distributions, we need to recall back theorem for Poisson distributions, where the first theorem, theorem 1.1, let x and y be independent random variables having Poisson distributions, where these x and y have a parameter mu and v respectively. So the sum x plus y has a Poisson distribution, so the parameter is also mu plus v. Okay, if you look at here, proving whether by the law of total probability, where the probability for x plus y is equals to n, then you will get the equation for the Poisson distributions for x and y is probability x plus y equals to n is actually equal with the original one under equations 1.1, but the parameter is mu plus v. Then you will get e to the power of negative mu plus v times with mu plus v to the power of n divided by n factorial. This is the desired Poisson distributions. Okay, to describe the second result, we consider first Poisson random variable n, where the parameter is mu greater than 0. Write n as a sum of 1 in the form, then you will get n equals to 1 plus and so on until n ones. So now look at here, considering each one separately and independently, erase with the probability 1 minus p and keep it with the probability p. So now we need to look at the second theorem, where the next theorem states and answer the questions in more precise wording. So the second question is where we have n. Okay, what is n? N is a random variable n, where let n be a Poisson random variable with the parameter mu, and conditional on n, let m have a binomial now, binomial distributions with parameter n and p. Then the unconditional distributions of M is also Poisson with the parameter mu times with P. Proving here is the verifications proceed via a direct applications of the law of total probability. This is just to recall back what you have learned in your mathematical statistics. Okay, and now you can see here our Poisson distribution equations where the difference is in terms of our parameter. Now our parameter is e to the power of negative mu p times with mu p to the power of k divided by k factorial. Okay, this is all about your mathematical statistics. Now we're going to enhance our Poisson distributions and we look at 1.2 Poisson process. Okay, the Poisson process entails notions of both independent and the Poisson distributions. So for this Poisson process, where we have definitions, but before that, I want to share with you topics. Okay, I'm going to use these two notes, textbook and also my notes. So for Poisson process, we can see here some extra informations where not in the textbook, where we're going to look at, of course, tadi kita dah tengok Poisson distributions. Now we're going to look at the Poisson process and subtopic 2. And later on from the textbook, we don't have merging and splitting. So I'm going to share with you merging and splitting Poisson process. From the textbook, we also have non-homogeneous Poisson process. This is also another special case for the Poisson process. Even they are special for time homogeneous, but there are some situations we can apply non-homogeneous Poisson process. And then from the textbook, we have law of rare events and Poisson process. Same goes to subtopic 6, distributions associated with the Poisson process. So, just now we talk about Poisson distributions, but why it is important to learn about probability distributions? Imagine that when we have a PDF or PMF of a random variable, okay, probability density functions or probability marginal functions, X, we can compute the probability of various events. We can look at the mean and variance of X without having to perform experiments and count from the data. Okay, sometimes we already have our distributions where we don't need to calculate our mean and variance from the original data because we already have the distributions where then we can calculate for mean and also for the variance. And when we have the probability distributions, we can simulate the real system and get the data. Okay, data are based on the simulations. So there are many experimental situations occur in which we observe the count of events within a set unit of time, area, volume, and length. For example, the number of cases of a disease in different towns, the number of mutations, set size region of a chromosome, the number of dolphin pod sighting along a flight path through a region, and so many other examples. So, in such situations, we are often interested in whether the event occur randomly in time or space. So, all these examples illustrate that the distributions of counts is useful in uncovering whether the event might occur randomly or not randomly in time or in space. Simply looking at the histogram, when you have all these numbers, you want to look in when you want to graph your data by looking from the histogram. So simply looking at the histogram is not sufficient if you want to ask the questions whether the event occur randomly or not. When you have the data, you can put it, your data in the histogram form, but okay, you cannot look at the event occur randomly or not. So to answer these questions, we need a probability model for the distributions of counts of random events that dictates the type of distributions we should expect to see. So before we go to Poisson process, because Poisson process is one of the counting process, so such processes are particularly simple. The states variable is just a count which increases by 1 at each transitions point. So a stochastic process here, instead of x, they apply using n. So sama saja. A stochastic process nt when t greater than or equal 0 is said to be counting process if nt represent the total number of transitions or event that have occurred in time 0 to t, and nt need to satisfy the following conditions. So under counting process, NT need to satisfy or must satisfy the following conditions. The first conditions where NT is a count variable at time 0 and 0 is equals to 0. If S at time S is less than T, so NS is less than NT. Okay. For S less than T, so NT minus with NS, this is we are looking at the increment, where this increment is equal to the number of events that have occurred in time between S and T. So a counting process is said to possess independent increment if the number of events which occur in disjoint, meaning that under this counting process, it is not overlapping or non-overlapping time intervals, and they are independent. Stationary or time homogeneous increment if the probability distributions of the number of events in the interval from time u to u plus t, meaning that the process at time u plus t or the counting process minus with nt depends only on t, okay, on the length of the time interval and not on its position on the time axis. Okay, this is time homogeneous. We are looking at the length of time interval and not on its position from one time point to another time point. So here, this is some figures or some typical graph to show you about the counting process, because this is not or non-overlapping. Here you can see the graph. Okay, at time t1 is non-overlapping at time t2 and so on. Okay. Now we move to Poisson distributions. Poisson distribution studies saya dah explain from the textbook. Okay, note si sama seperti our textbook. Okay, now we proceed with the Poisson process. So Poisson process, this is similar with our textbook. Poisson process is the stochastic process in which events occur continuously and independently of one another. This Poisson process is important as discrete time Markov chain. Okay, but Poisson process in continuous time model. So three different characterizations, independence assumptions in all cases, where under Poisson process, number of events in an interval is Poisson distributed with independent increment and constant intensity for event. And number three, interval between event are exponentially distributed. Okay, itu adalah ciri-ciri characteristics of the Poisson process. Okay, tengok textbook, ada lagi information dia. Okay, definition dia belum lagi. Okay, ini definition dia. So I'm so sorry, yang ni dia pakai delta. To make it easy to understand, I put it in H. Tapi sama je, yang double ni jangan risau. Pakai delta, saya pakai H. So Poisson process dia ada limit daripada Bernoulli distributions or Bernoulli process. So Bernoulli is one of the statistical distributions. You can refer to our actual table and formula. Sekejap . Okay. Sekejap . So suppose that we would like to model the arrival. Contoh ini ada timeline from 0, H, 2H, 3H until ... So this model, would like to model the arrival of event that happen completely at random at a rate lambda per unit time. Here is one way to do this. At time t equals to 0, we have no arrival yet. So meaning that at time 0 and 0 equals to 0. Because as mentioned, counting process at time 0, the counting process is equals to 0. So now we divide the half line, okay, into tiny sub interval. instead of kita ada 0, 1, 2, bayangkan kita ada length yang lebih kecil di mana kita ada tiny sub interval, we put it as H. Okay, daripada 0 ke 1 tu, dalam tu ada anak-anak dia lagi. Maksudnya, contohlah 0 ke 1 jam. So, dalam tu ada minute or second. So, they represent H, a tiny sub-interval of length H. So, each sub-interval correspond to a time slot of length H. So, thus, the interval are, if you look at here, we have 0 to H, H to 2H, 2H to 3H, and so on. More generally, the kth interval is, we can say like k minus 1h to kh. We assume that in each time slot, we toss a coin for which the probability h equals to p. Okay, kalau kita toss a coin, probability h, maka dia adalah p ataupun dia kita denote sebagai lambda h. Sebab tadi dia kata rate dia lambda per unit time. So unit time kita h, maka probability p equals to lambda h. If the coin lands head up, we say that we have an arrival in that sub-interval. So otherwise, we say that we have no arrival in that interval. So next figure, we show you this process where we have an arrival at time t equals to kh if the kth coin flip results in a head. So this is a figure 2. If you can see here, the first arrival, T1, we have H, tail, and then H for the second arrival, tail, head for the third arrival. So this Poisson process is actually has a limit of a Bernoulli process. So now let, the process or the counting process at time t be defined as a number of arrival, meaning that here we declare as a number of hits from time 0 to time t. There are n t divided by h slot. Just now we have in terms of h in the interval 0 to t, and the nt is the number of hit in n coin flips. Okay, so we conclude that, kalau you tengok Bernoulli distribution, dia ada satu arrival sahaja. Okay, tapi kalau banyak variable daripada Bernoulli, is actually they become binomial distributions. So you can refer to we can refer to any statistical textbook, or you can refer to Carlin, where Carlin textbook, we also in chapter 1, dia ada about Bernoulli, dia ada about binomial. Okay, so again, kalau you tengok Bernoulli and binomial, dia ada relationships. So for more details, you can refer back to your mathematical statistics. So since here we have n coin flips, maka dia ada, and they've processed at the limit of a Bernoulli process, so they can conclude that the count process at time t follow binomial with the parameter np. So now, just now we say that p equals to lambda h, so np equals to n times with lambda h. Then here we have time slot t divided by h, so n equals to t divided by h, maka t divided by h time with p, which is lambda h, you will get our parameter is equals to nt. Okay, so when h approach to 0, h tu kan timeline yang paling kecil, so kita kata h tu sedekat-dekat yang kecil, yang near to 0. So when h approach to 0, the probability mass functions of nt converges to a Poisson distributions with rate lambda t. Okay, daripada binomial, even they are in Poisson process, sebabkan h approach to 0, so this distribution converges to a Poisson distribution with rate lambda t. More generally, we can argue that the number of arrival in any interval of length tau follow a Poisson lambda tau distribution has h approach to 0. Ini adalah kenapa nanti you nak pakai Poisson process. Okay. Tadi, kenapa kita dapat lambda t? Because it will relate with our Poisson process. A collection of nt of random variable index by time t is called a continuous time stochastic process. Furthermore, we call the counting process nt a Poisson process. Now, if they have 4 conditions, starting with time 0 and 0 equals to 0, the process nt takes a non-negative integer from 0, 1, 2 for all t greater than 0. B, the increment n okay, at time t plus s minus with n at time t is surely non-negative for s greater than 0. Okay, the increment, okay, where we look at the increment now, n at time t plus 1, n at time t plus, sorry, n at time t2 minus with n at time t1, and so on until n at time tn minus with n at time tn minus 1. And these all increment are independent from one time point to another time point. And the increment between n plus ts minus with n plus t has the distributions which is dependent on the value s greater than 0 but independent of t greater than 0. So counting process, which is a stochastic process satisfying A and B, is called a counting process, in which nt represent the total number of events count up to time t. Okay, kalau kita nak tengok Poisson process is actually also one of the counting process, di mana Poisson process memenuhi syarat-syarat A and B, while the properties C and D are respectively called independent and stationary increment. So particularly by applying A and D, we can obtain the probability for n at time t plus s minus n at time t equals to k is actually the length where we are looking at the probability for n at time s equals to k. So far, any questions? Adila Rosli, do you have any question? Adila Rosli? Adni, do you have any question? Adni?
No, no, madam.
Okay. Now, we look at one exercise. So, the notes that I explained just now from the slide is actually similar with our textbook for the Poisson process, where they have, kat sini dia ada 3, tapi saya tambah satu lah. Saya kembangkan independent and also saya kembangkan definition from 1. Okay, where we have a Poisson process, now we need to calculate our equations from 2 here, where we have, tadi kita kata textbook pakai X, note saya pakai N. Okay, just to differentiate Markov chain and also Poisson. Tapi textbook dia belasah semua X. So you don't get confused. X3 ke N3 ke dia sama. Okay, for the Poisson process, when they has the Poisson distribution, macam note study dia kata kat sini, dia ada counting process, maka kita kata dia punya equations adalah lambda t. Tadi kita dah proof mana kita dapat lambda t. So lambda t to the power of k times with e to the power of negative lambda t divided by k factorial. Since Poisson process follow Poisson distributions, maka mean dia adalah lambda t, the parameter, and same goes to their variance, which is also lambda t. Okay, itu adalah definitions for Poisson process. Now we take a look at the example. So example here, we have 2 example here, where defect occur along an undersea tape cable according to a Poisson process of rate lambda equals to 0.1 per mile. They have 2 questions here. What is the probability that no defects appear in the first 2 miles of cable? B, given that there are no defects in the first 2 miles of cable, what is the conditional probability of no defects between mile point 2 and 3? Dia dah bagi jawapan lah. So, another example, customer arrive in a certain store according to a Poisson process of rate lambda equals to 4 per hour. Given that the store opens at 9 a.m., what is the probability that exactly 1 customer has arrived by 9:30 and a total of 5 have arrived by 11:30 a.m.? So I give you 2 minutes. Go through these 2 examples, and then we're going to discuss these 2 examples. Okay, let's take a look at example, the first example, where we have Poisson process with the rate 0.1 per mile. So what is the probability that no defects? Okay, so no defects meaning that k equals to 0. So the first question here, uh, to answer here, we observe that x2 has a Poisson distributions. So at timeline from 0 to 2, there is no defect. Okay, kalau dia kata from timeline, sekejap print screen lah. Saya punya Google Drive problem. So you all better nak download ke, nak apa, simpan notes ke apa, you simpan sebab dekat group part 6 saya dah dah hilang. Okay. So here if you look at here question A, saya share. So for these questions, A, it shows that from time 0 until time 2, ada no defects appear from 2 miles of cable here. So 2 minus 0 is at t equals to 2. And that's why your probability for x, actually, x2 minus with x0 equals to 0. So by time homogeneous, this is x2 equals to 0. Then you can solve using e to the power of negative lambda t, lambda formula dah. Mana pergi kau, you all lupa pula formula. Kalau you tengok buku textbook tu, kita kata lambda t to the power of k, e to the power of negative lambda t divided by k factorial. Saya terbalik tapi sama sajalah. Okay. Lambda t to the power of k divided by k factorial. Then you will get e to the power of negative 0.2. Dapat? Farisha, you dapat tak jawapan 0.8187? Farisha ada? Farisha tak ada. Adlina Najiha, you dapat? By using the Poisson process, you're supposed to get e to the power of, because of k equals to 0. So you boleh cakap kosong factorial adalah kosong. Sorry, 1. So dekat sini adalah e to the power of negative 2. Apa-apa? Negative 0.2. Farisha tak ada? Nur Kasrina, did you get the answer 0.8187?
Yes, madam.
Okay. Okay, next soalan kedua. Given that there are no defects in the first 2 mile of cable, what is the conditional probability of no defects between mile point 2 and 3? So here, we use the independence of x3 minus x2 and x2 minus x0. Okay, thus the conditional probability is the same as the unconditional probability. Okay, so kalau dia tengok kat sini, dia nak tengok mile point 2 and mile point 3. Di mana mile point 2 and mile point 3 also no defect. And that's why the probability of x3 equals 3. The probability of x3 minus with the probability of x3 minus with x2 equals to k no defect, meaning that equals to 0. And x3 minus x2, kita nak tengok increment, maka dia adalah x1. So x1 equals to 0. So e to the power of lambda t, negative lambda t times with lambda t to the power of k divided by k factorial, you will get e to the power of negative 0.1. Boleh?
Boleh.
Okay. Next, we move to uh, our textbook. The second example, where second example shows you non-homogeneous pula. Kenapa ni? Customer arrive in a certain store according to a Poisson process of rate lambda equals to 4 per hour. Given that the store opens at 9 a.m., what is the probability that exactly one customer has arrived by 9:30 and a total of 5 have arrived by 11:30? So you need to draw your timeline. So when you draw a timeline, measuring time t in hours from 9 a.m., we asked to determine probability of x equals to half equals to 1 and x 5 divided by 2 equals to 5. So we use independence of x 5 divided by 2 minus x half and x half to reformulate the questions. So probability of x half equals to 1, x 5 divided by 2 equals to 5. It's actually equals to the probability of half equals to 1 and half minus with x5 divided by 2 minus with x half equals to 4. Then you will get the answer for the second example is 0.0154965. Any questions here for second example? Amir Zakwan, ada apa-apa soalan example 2?
Tak ada.
Okay. Sama saja seperti you punya Poisson distributions. Yang membezakan sini, we are based on the increment and we are also based on lambda t has our parameter. Okay, since you don't have any questions, let's take a look at exercise. One exercise. Simple exercise. Okay. 1.7. Suppose that customer arrive at a facility according to a Poisson process having rate lambda equals to 2. Let xt be the number of customers that have arrived up to time t. So determine the following probabilities and conditional probabilities. So now we have A, B, C, and D. So I give you now is 10:51. I give you until 11. Try to answer 1.7 A, B, C, and D. Okay. Again, if you look back at these questions where they give you the parameter, which is lambda equals to 2, and then we let xt, now our xt be the number of customers that have arrived up to time t. So determine the following probabilities and conditional probabilities. For A, where they ask you at time 1, xt, where t equals to 1. So the probability of x1 equals to k, which is 2. So again, A is the probability of x1 equals to 2. What do you get? The answer for A, 1.7A, Muhammad Khalis. Apa jawapan anda, Muhammad Khalis Akif? Tak ada, Muhammad Khalis Akif. Tak ada, kita pergi ke Nur Adawiyah. What is your answer, Nur Adawiyah?
Kosong point 2707.
0.2707. Okey, yang lain dapat sama seperti Nur Adawiyah?
Sama.
Sama, Alhamdulillah. So then we can go to the next questions. Well, next questions is now dia bagi you ada dua. Probability of x1 equals to 2 and x3 equals to 6. Dapat apa? Syaril, dapat apa Syaril?
0.0529.
0.0529. Yang lain dapat sama ke? 0.0259.
0.0529.
Okay. What about Mariam Jamila? Did you get the same answer dengan sama seperti Syaril?
Sama, madam.
Okay. So 1.7C. Ilya, what is your answer, Ilya? Ilya tak ada. Ilya tak ada. Amni?
Kosong point 3292.
0.3292. Yang lain dapat sama ke? 0.3292? Sofia?
Sama, madam.
Sama. Okay. Tapi sebenarnya C ni dia special case. Sebab dia suruh, if you draw a timeline, zero lah ya. This is 1, this is 3. Dia kata given at time 3 where they have 6, but they ask you to find at time 1 where they have 2. Tak apa, kita simpan lah. Jawapan ni 0.3292. Next, D. Wan Muhammad Amal. What is your answer, Wan Muhammad Amal?
D, madam.
D.
0.1954.
0.1594. Sama ke dengan yang lain?
1954, madam.
1954. Any questions so far for A, B, C and D? Tak ada. Okay, then we can move to next.
Oh, madam.
Ya, saya.
Kalau madam tunjuk yang C dengan D boleh tak?
C. You dapat berapa C?
Saya tak dapat.
Okay, nanti saya minta kawan you snap. Tadi siapa ya yang bagi C dengan D? Boleh tak share gambar dekat WhatsApp group dulu untuk Siti Saidatul tengok dulu. Tapi C sebenarnya dia ada special case lah. Tapi tu saya nak tahu jawapan juga. Bukan jawapan, saya nak tengok working. Saidatul boleh bagi working Saidatul juga. Apa Saidatul dapat? Walaupun sekerat jalan ke, separuh jalan ke pun boleh. Okay. Kalau yang 3 ni tak apa, kita tunggu jawapan. Tak apalah, kita bagi 4-4 lah. A, B, C, D. Tadi yang bagi jawapan, you snap je gambar working you masuk dalam group kelas. Itu cara kita discuss dengan kawan-kawan. Boleh? Nanti you snap. While waiting for your friend nak snap. Tu ada seorang dah. Amni dah share. Thank you Amni. Apa nama? Siti Saidatul. Nanti you tengok dulu. Lepas tu we can get some discussions lah after this. Boleh?
Boleh, madam.
Okay. Yang C tu nanti kita tengok balik. Sebenarnya C tu dia ada sedikit jalan kerja. Tapi kita simpan dulu jawapan 0.3292 ni sebab ramai yang dapat lebih kurang sama 0.3292. Okay. Kalau A, kalau you tengok kat sini dia direct lah. Dia kata from time 0 until time 1 ada 2 customer yang arrive. From B, dia kata 0 hingga 1 ada 2 dan sampai 3 ada 6. Maksudnya 0 sampai 1 ada 2, 0 sampai 3 ada 6. So maksudnya 1 sampai 3 ada 4. Okay, untuk C 0, 1, 3. Sama juga kat situ. Maksudnya kita cari probability for, tapi yang ni dia special case. Macam mana kita nak cari X1 tolak dengan X3? Sebab dia beri kita 3 kat belakang. And that's why you need to explore more. And we're going to look at our friend. Tak kisah salah ke betul, tapi dia try to attempt. And I really appreciate those who try to attempt and try to answer the questions. Okay. Kalau untuk yang D, dia 0, lepas tu given 1. Macam tadi jugalah. Given 3 ada 6. So kat sini kita cari probability of X3 tolak X1 sama dengan 6 tolak 2 adalah probability X2 equals to 4 for question D. Yang ni you tengok macam kita punya tadilah example sebab dia ada N. So you kena ambil X1 darab dengan X3 tolak X1 which is 6 minus 2. So X1 darab dengan X3 tolak 1. While waiting for your friend to share their answer, so you can try and seed jawapan you untuk dapat tak seperti kawan you dapat. Okay. I will continue with our textbook. Mana textbook? 1.7 patah balik. Sampai sini. So for my notes ada lagi tak apa-apa tambahan? Oh, merging. Okay, dalam textbook tak ada merging. Tapi I try to share with you. Ada isu juga mengenai dia merging and also its splitting. So for merging and splitting Poisson process, you can see here when we have 2 arrow here, N1T, N2T, both have their own rate, lambda 1 and lambda 2, going to merge and become NT. So now our rate is lambda 1 plus lambda 2. Same goes to our theorem 1.1, where we have X, we have Y, then our X plus Y, which is our NT, and our rate is also, we need to plus lambda 1 plus lambda 2. This is we call as a merging Poisson process with rate lambda 1 plus lambda 2. Okay, kalau merging, kita boleh ada lebih daripada 2. Sebab kita tahu merging dia, kalau ada 3 pun dia merge lah. So, lambda 1, lambda 2, lambda 2. Splitting dia ada problem sikit. Nanti kita tengok. Cuma kita limit our discussions up to, we can split up to 2. If we want to split more than 2, then we need to do some extra task lah. but this is not in our syllabus. We just want to share that they can split by 2. But before that, take a look at the merging. Merging is to consider two Poisson processes with rates lambda 1 and lambda 2 and define a new process with an arrival whenever an arrival occur in either process. So this new process is also Poisson with arrival rate around lambda 1 and lambda 2. Example, the arrival of customer wishing to make a deposit at a bank teller window is Poisson with rate line per hour, and the arrival of a customer wishing to make a withdrawal. Okay, satu nak deposit, satu nak withdraw, with a different lambda rate, which is 9 per hour and 6 per hour. So the aggregate arrival of customer at this bank teller window is Poisson, when 9 plus 6 is 15 per hour. So now imagine that we have this figure 4, merging two Poisson process. We let N1T and N2T be two independent Poisson processes with rate lambda 1 and lambda 2 respectively. So now we can define that our merge process NT is N1 plus N1T plus N2T. So the random process NT is obtained by combining the arrival in N1T and N2T, as you can see in figure 4, where N1 in the white dot with the white dot and N2 with the black dot. And then you can see here, merge process NT dikombinkan white dot and the black dot. So we claim that NT is a Poisson process with rate lambda, where lambda is the combinations between lambda 1 and lambda 2. Okay, so next, since N1T and N2T are independent and both have independent increment, we conclude that NT also has independent increment. Consider an interval of length tau, where imagine that I equals to T plus T to T plus T tau. Then the number of arrival in I associated with N1T and N2T are Poisson with the lambda 1T and Poisson lambda 2T, tau, and they are independent. So therefore, the number of arrival in I associated with NT, just to say that they have lambda 1 plus with lambda 2T. Same goes to the Poisson process. Just because of they come from the merging process, they also have the sum of two independent Poisson random variables. So merging, we can write our N1T, N2T until NMT, BM independent Poisson processes with rates lambda 1, lambda 2 until lambda m. So NT is just a combination of N1T plus N2T until NMT for all t between 0 to infinity. So NT is also a Poisson process with rate lambda 1 plus lambda 2. Here I have made some mistake. You twist 2 plus lambda 1 plus lambda 2 plus dot 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 plus lambda m. Okay, kat situ terhilang pula saya punya dot. Splitting, tadi daripada 2 masuk 1, sekarang daripada 1 pergi ke 2. Kenapa saya kata boleh 2 saja? Sebab we based on the probability. One with P, another one with 1 minus P. If we have a lot of information in terms of the probability, meaning that they can go to maybe P, 1 minus, kita ada P, dan kita ada nilai dia lagi, P1, P2, P3, then we can split into 3. So for here, we can say that splitting is a conversely, consider a Poisson process with arrival rate lambda and split, where each arrival are P and Q adalah 1 minus P. So kita ada P, kita tahu 1 minus P. Tapi kita ada banyak P, kita boleh splitkan more than 2. The process of P arrival is a Poisson process with rate P lambda, and the process of Q 1 minus P arrival is a Poisson process with rate Q and lambda. Contoh, if the arrival of vehicle at an intersection is Poisson with rate 20 per minute, and 30% of the vehicles are trucks, then the arrival of trucks is a Poisson process with rate 0.3 times with 20 per minute. So maka dia adalah 6 per minute untuk truck. Splitting, NT be a Poisson process with rate lambda. We divide NT to two processes, N1T and N2T, in the following next figure, figure 6. For each arrival, a coin with probability of head P is tossed. If coin lands head up, the arrival is sent to the first process, N1T, otherwise it is sent to the second process. So the coin tosses are independent of each other and are independent of NT. Then, N1T is a Poisson process with rate lambda p. N2T is a Poisson process with rate lambda 1 minus p, and both are independent. This is a figure 6 where we can see here in the middle is the process NT that we're going to split based on our head and coins. So head and tails. Kalau dia head, dia pergi ke process 1. Kalau dia tail, dia pergi ke process 2. For example, then we're going to split our Poisson process to two independent Poisson processes. Any question for merging and splitting? Muhammad Danish Afiq, do you have any question, Danish Afiq? Danish tak ada. Nur Dania binti Sahrul Niza, ada soalan? Nur Dania tak ada. Nurul Atika, do you have any question? Nurul Atika Muhammad Sobri? Pun tak ada. Siti Saleha, do you have any question? Siti Saleha?
No, madam.
Okay. So, kita nampak kawan kita dah share. D, C, B, tinggal A je belum. A tadi siapa ya? Tolong share kat kawan. Okay. Kita continue ke non-homogeneous. Okay. Non-homogeneous Poisson process, even we say that, and they mentions that Poisson process follow time homogeneous, so dia juga boleh jadi keadaan non-homogeneous Poisson process. Okay, so tak banyak yang berlaku, tapi boleh berlaku di mana when let NT be the number of customer, contoh arriving at a restaurant by time T. We think that the customer arrives somewhat randomly, so we might want to model NT as a Poisson process. Okay, kalau you tengok dekat, tak boleh yang tu kita boycott ni, contohlah. Kedai apa food court, fast food, satu kedai fast food yang ada drive-thru. Ramai orang akan pergi drive-thru pada lunch hour. So, the rate of customer arrive during lunch hour is higher compared to after lunch hour, meaning that from 12 to 2, the rate of the customer is higher compared to rate 2 to 5, contoh. So, however, we notice that this process does not have stationary increment. The Poisson process, as we define, is a characteristics by a constant arrival rate lambda. For example, we note that arrival rate of customer is larger during lunchtime compared to, say, that at 4 p.m. contoh. So for this scenario, we might model NT as a non-homogeneous Poisson process. It means that a process includes all the properties of the Poisson process except for the fact that it rates not in lambda constant but in lambda equals to lambda in the functions of t. Okay, it is often useful to consider a more general types of process in which the arrival rate varies as a function of time. Non-homogeneous Poisson process with time varying arrival rate lambda in the functions of t or in the bracket t is defined as a counting process NT t greater than 0, which has the independent increment property, and for all t greater than 0. Now, setiap time tu berbeza-beza, we need to consider our little h or h time greater than 0. Also satisfied at time 0, the process is equals to 0, and t has independent increment, and for any t is between 0 to infinity, we can see here in the previous class, we talk about delta t. So, delta t samalah delta h, samalah h ni kita nak cakap. Kalau you tengok dekat kotak kecil kanan tu, definitions of 0h, macam saya cakap dulu, if the functions h is 0h, then limit h approach to 0 is actually fh divided by h equals to 0. This little 0 notations means that the functions fh approaches 0 faster than h itself approaches 0. Itu yang maksud semalam dalam topik 4. Okay, kita apply benda ni, 0h ni, dalam kita punya equations, when we want to find the probability of n for t plus h minus nt is equals to 0. Okay, bayangkan kalau dia equals to 0, maka kita kata 1 minus h lambda t plus 0h. Probability ada seorang, tapi probability probability ada equals to 1, confirm ada 1, probability sure 1, but they have some informations of h with the lambda t. But if you say that, sebab apa? Probability yang kosong arrival dalam masa yang kecil itu, the probability is near to 1. Okay, when the probability n t plus h minus with nt, arrival is 1, so the probability should be smaller than the above one. Because kebarangkalian ada satu customer datang adalah less than 1. So lambda h lambda in the bracket t or in the functions of t plus with 0h. So, kita nak kata dalam 1 second tu, kalau nak kata probability lebih daripada atau sama 2 adalah kosong lah. Sebab kita tengok dalam time point yang sangat kecil dekat drive-thru tu. So, that's the reason in 3, where for t greater than between 0 to infinity adalah equals to 0, equals to 1, and equals to or greater than 2. So, the rate lambda, kita kata kita consider kalau customer dalam masa 1 second tu, dekat drive-thru tu, yang fast food tu nak entertain, it's near to 0. Kan? Kita duduk kat situ pun dah berapa minit nak order semua kan. So, the rate lambda is a Poisson process, and in the bracket t is the proportionality constant in the probability of an event occurring during an arbitrarily small interval. So, let's say we look at yang kalau dia ada satu customer. So, the probability of n t plus h minus nt equals to 1. So, we say by using that our Poisson process equations. So, we will get lambda in the bracket h e to the power of negative lambda h divided by 1 factorial. Then end up you will get it is equals to lambda h plus 0h, where 0h we can say or we can ignore, or it is equals to 0. Then that's why we will get our probability equals to lambda h. So we conclude that the probability of nh, okay, because we are looking at the increment, so nt plus h minus nt is actually t minus t plus h. Then you will get nh, which is equals to 1, equals to lambda h plus 0h, where 0h denotes a general and unspecified remainder term of smaller order than h. So if h is small, the probability of a single arrival is in approximately, while the probability of more than one arrival in this interval is negligible. So the non-homogeneous Poisson process does not have the stationary increment property. Okay, dia punya increment tu tak sama, tak stationary. Then we need to consider our lambda or our rate in the functions, where lambda in the functions of t that vary with time. Lambda dekat time 2 tak sama dengan lambda dekat time 3, because they are vary with time. For a non-homogeneous or non-stationary Poisson process, to distinguish it from the stationary or homogeneous process, what that we primarily consider. So for non-homogeneous Poisson process with rate lambda in the bracket T, the number of arrival in any interval is a Poisson random variable. Its parameter can depend on the locations of the interval. More specifically, we can write our equations where xt plus s minus with xt follow Poisson with the interval t to t plus s lambda mu du. Maksudnya kita kena cari kita punya new lambda, our lambda in the functions of t. Non-homogeneous, just to recap what I've mentioned just now, non-homogeneous process. So this is what I explained just now about the probability, where here we take a look at example where demands on the first aid facility in a certain location occur according to a non-homogeneous Poisson process. Now look at here, we have our lambda in the rate functions, where lambda in the functions of t is divided by t between 0 to 1, t between 1 to 2, and t between 2 to 4, with the 2t, 2, and 4 minus t, where t is measured in hour from the opening time of the facility. What is the probability that 2 demand occur in the first 2 hours of operations and 2 in the second 2 hours? Since demand during this joint interval are independent random variables, we can answer the two questions separately. Kenapa kita kena cari separately? Sebab kita kena kira soalan dia nak what is the probability that two demand occur in the first 2 hours, which is from 0 to 2, and another hour, second 2 hours, which is 2 to 4. So 0 to 2 ada satu equations, 2 to 4 ada satu equations. For the first mean for the first 2 hours, because of we have 0 to 2 tu dibagi dengan 2, di mana kita ada 2t, kita ada 2. So we need to find our new parameter, which is here we allocate that it is equals to mu. Just to differentiate between lambda and mu. Lambda t tu dalam functions, mu adalah our new lambda when we consider our rate functions of lambda t. So kita kena integrate dulu our mu. So 2t is between 0 to 1. So we integrate 0, 1. 0 to 1 with respect to 2t dt plus integral from 1 to 2 with respect to 2 dt. Then when you integrate, you will get it is equals to 3. Now our parameter is equals to 3. Our mu is equals to 3. Then we can calculate our probability, where the probability for x2 equals to 2 adalah e to the power of negative mu. Mu ni kita dah consider lambda t. So e to the power of negative 3, 3 to the power of 2 divided by 2 factorial. So our probability is 0.2240. And the second 2 hours, where this is between 2 to 4, then you need to integrate from 2 to 4 for 4 minus t dt. When you integrate, you will get our lambda t, or our new parameter is equals to mu, which is equals to 2. Then the probability for x4 minus x2 equals to 2. Maka kita kata kita punya tu adalah x4 tolak x2 adalah 2. So e to the power of negative 2, 2 to the power of 2 divided by 2 factorial is 0.2707. Okay, itu adalah cara kita kira jika dia adalah non-homogeneous Poisson process. Okay, dekat bawah ni adalah lebih kepada explanations of your xt lah. Okay, kita nak tengok kat sini, change of S sama saja seperti yang saya explain dalam PowerPoint. Okay, Cox tak ada dalam our syllabus, but Cox you can more in details dalam survival models. Habis dah chapter 1. Any questions? Nurman Arif, do you have any question, Nurman?
No, madam.
Okay. Nur Eliana Batrisha, do you have any question? Nur Eliana Batrisha?
Tak ada, doktor.
Okay. Nur Hanani, do you have any question? Nur Hanani?
Tak ada, doktor.
Okay. I think that's all for today. So by next week, we're going to look at next law of rare event and also some Poisson versus binomial. And after that, I think dalam textbook ada law of rare events juga. Kenapa dia stuck? Okay. Boleh go through law of rare. Kalau nak buat soalan, buat je passing exams questions. You can look at the law of rare events. Lepas tu kita akan pergi ke law of rare events and the Poisson process. And after that, we will go to another lagi subtopic. Ada lagi ke dah habis? A little bit on the distributions associated with the Poisson process. Kita akan cover sampai sojourn time. Okay. Since you don't have any questions, I think that's all for today. You all punya tarikh konvo bila? Kalau tapah bila?
Tapa 20.
20 hari apa tak kena kelas kita
Selasa kot.
Oh, Selasa. Selasa kelas saya. Selasa kelas. Pagi petang? Lah pagi petang mestilah you nak dengan parent you kan?
Pagi.
Oh, pagi kelas kita lah. So, tak boleh buat kelas lah 20 hari bulan.
Tak boleh.
Seremban berapa hari bulan?
25.
25. Okey, Ahad. So, 20 lah. 20 saya tak buat kelas tapi saya share video. Okay, if you have a free time, maka hari Rabu tu 21 tu kita video tu adalah video ordinary differential equation di mana kita nak pakai video tu. Maksudnya knowledge tu based on your calculus. So I'm going to share with you knowledge ataupun information through you punya calculus balik lah, nak recall balik you punya calculus. So you boleh, I share awal sikit lah, I share on Monday ke supaya you all ada extra time kalau you busy dekat 20 hari bulan. So thank you very much. Bolehlah buat past year exams questions juga. Assalamualaikum.
Waalaikumsalam.